please share your screen?
Yep.
Yep, that looks good. You can go ahead.
Cool. Okay. So hi, yeah, I'm Zach Vanderbosch. I'm a graduate student at the University of Texas at Austin right now, about to finish up and started postdoc at Caltech, working with the ZTF group there. But today I will be talking about white dwarfs with transiting planetary debris and how we can discover and characterize them in the era of large time domain surveys, at least much better than we have been able to before. So this is work I've done over the past 2 to 3 years, most closely with J.J. Hermes, who's at Boston University, and Joseph Guidry, who is an undergraduate here, but is moving on to grad school to work with J.J. Hermes. But there's a lot of people in the audience I've worked with on this stuff who I owe many thanks for all the help and contributions along the way. So I'm not going to spend too much time on the background, but I do want to give just a brief history of planetary debris around white dwarfs and how we came to this conclusion. It all started with the detection of metals in the atmospheres of white dwarfs, which, since white dwarfs have such strong gravity, they shouldn't be there unless they're being actively accreted. Over time, these went from being assumed to accrete from the interstellar medium to being accreted from disrupted planetary bodies around white dwarfs. We also see this in the form of infrared excess in a smaller number of white dwarfs, and then additionally in the form of metallic emission lines due to a hot gaseous component of that disk. And then most recently, we've discovered transiting planetary debris. So I'm sure everyone here is familiar with this system. It's pretty famous. So this is WD 1145, the first planetary debris system found. And you could spend a whole talk on this one system, but I just want to highlight a couple of characteristics of it that indicate how dynamic this system is. So this system has debris in orbits of 4.5 to 4.9 hours. And that's pretty close to the Roche limit of the white dwarf. And it's also metapolluted, has an infrared excess, and exhibits circumstellar absorption. This plot on the top left is from Bruce Gary's monitoring over many years in combination with data from several publications showing how the total transit activity varies by 1 to 2 orders of magnitude over months and years. So there's a lot of physical processes that are happening in this system, collisions, potentially sublimations of dust that are causing the overall transit activity to vary. And then in addition to that, we see the circumstellar velocity profiles vary on timescales of years, most likely due to some precession activity. And then we also see in-transit bluing due to changes in circumstellar absorption strengths as whatever clouds of material are occulting the disk and the white dwarf simultaneously. So a lot of stuff is going on in the system. It's very dynamic. It's pretty well characterized, although we still don't quite understand exactly the origin of the debris and what physical processes are most important in terms of its continued production of debris. But most likely it's some combination of collisions and sublimation. But this is the only system we knew of for quite a long time, from 2015 until just last year. And so we don't know yet if this system is necessarily characteristic of the class of transiting planetary debris systems. So really we need to find more. But that's a challenge because these are quite rare and hard to find. But it's necessary because they probe a very different part of the tidal disruption evolutionary process. So this is a plot from Van Lieshout et al. 2018, which nicely summarizes sort of this whole process of getting planetary objects from far away towards in close to the white dwarf, and then the physical processes that govern different stages of evolution. So far, all of the metal pollution, dust disk, gas disk, and even WD-1145 are probing a small part of this particle size versus radial distance diagram on top, which is kind of encapsulated by this red box here. And there's a lot of physical processes that we can probe and try to understand here, such as collisions, sublimation, accretion, and diffusion. But it leaves a large part of this space pretty unexplored, especially over here. And this is sort of what we would like to understand better, at least from an observational standpoint. We just want more constraints in this region so we can better compare with theory. The two new systems that we found since 1145 do probe further into this space. And so we're doing everything we can to understand the characteristics of these systems and how they might constrain the tidal disruption process. But we're also trying to keep an open mind here because there might be other processes such as the rotational breakup of asteroids, which doesn't require slight or as high eccentricity orbits. But yeah, we just want more observational constraints in this region. And that's what these transiting planetary debris systems can provide for us. But like I said, it's a game of numbers and finding them is hard. But with Gaia and ZTF, two just of the most easily accessible for large numbers of objects, we can really begin to discover more of these systems in a faster rate than we have been able to before. So Gaia currently gives us about 360,000 high probability white dwarf candidates, and ZTF is observing the northern sky every 3 nights or even less in certain regions for certain parts of their surveys. And this is, the combination of these two is a really powerful way to try and identify more of these systems. And the way we're currently doing this is developing a set of variability metrics, which just broadly identify variable white dwarfs in the Gaia catalog. So for instance, Nicola, he recently published a paper showing how you can use Gaia excess error to identify variable stars. And we also did this in a paper by Joseph Guidry earlier this year, which used a similar method to just identify stars or white dwarfs that have more variability than they ought to at their particular brightness. You can do this with just Gaia, but Gaia is it's limited in time and doesn't have nearly as dense observations as ZTF does. And so when you combine these two, you increase the time baseline where you can see variability, and you also have the ability to use a wider range of variability metrics that might be able to identify transiting debris systems more easily. So this plot here is just showing a variability rank that we've developed, which is a combination of ZTF and Gaia metrics. And on the right is a log-GT effective diagram showing the top 1% sample, which are those colored red on the left panel as well. So just the top 1% most variable according to this rank. Most of them appear in the ZZ SETI instability strip, which is good. That's where you would expect to find them. But we're not interested in ZZ SETIs. We want to find all the other interesting systems, including the transiting debris. So for the most part, we looked outside of the instability strip and have continued to do so to try and find these. And essentially, this is the result of our search so far. So WD1145 in the middle is now the only object out of these 8 where it wasn't discovered using ZTF or Gaia to identify it first as a variable star. On the left is all the ZTF light curves for these 8 objects, and on the right are high-speed follow-up with the McDonald 2.1 meter to highlight how the timescales of variability for these systems are covering a very wide range from, tens to even hundreds of days for these top 4 systems to minutes and hours for the bottom 4 systems. And 3 of these, only 3 so far, have confirmed orbital periods for their debris, and we would like to increase that number. But some of these systems, which you might expect we could get an orbital period for, like the yellow light curve here, have so far not shown us any conclusive orbital period, even though there's quite a lot of dips. And then the orange object only has 1 dip so far in 3 years of monitoring. So yeah, it's quite a challenge to characterize some of these systems in detail, but we're working on that. And we can also use these metrics, like I mentioned before, to kind of distinguish some of these objects. So now they're color-coded, the top % by their variability type, so the pulsations, cataclysmic variables, or the transiting systems, which are broken up by long and short period. And as you can see, they're mostly outside the instability strip. And if we compare some of these different metrics we use, we can kind of see the transiting debris systems group up somewhat in certain regions. So for instance, comparing point-to-point scatter and standard deviation, the long period transiting debris systems are in somewhat of a unique space and might be able to be identified that way. And in the bottom 2 panels, we're showing the skew. And this is the first time we've used a metric that actually looks at the distribution of flux values and whether they're more on the bright side or the dim side with respect to the mean. And again, because we're dealing with typically, flux dips in the light curves, the skew tends to pick these out pretty easily as well. Not all of them, but some of them occupy a relatively unique space compared to pulsating white dwarfs or cataclysmic variables. So in future surveys such as LSST, which will have similar time sampling compared to ZTF, though perhaps a little bit sparser, we might be able to identify these systems a little more easily just using variability metrics of the light curves. So yeah, from here, I just kind of want to go into a couple of the new systems, so J0139 and J0328, to kind of highlight how they're different from 1145 and why that is important and why that kind of makes the case for why we need to keep finding more of these systems and characterizing them, because as a class of objects, they are still relatively poorly understood. And their observational characteristics can vary quite a lot between objects. So this is J0139 with the photometry updated compared to our publication, which was mainly just the first 4 transits stopping here. And since then, we've observed about 3 or 4 more transits. The major characteristics here are obviously its long period, which is like an order or 2 orders of magnitude longer than 1145, and would suggest a very eccentric orbit if this is still coming within the Roche limit at periastron. If we take this orbit and fold it on the orbital period, with our publication, we found that the orbit was actually pretty stable at about 107 days. But the very next orbit we observed came 20 days earlier than we expected it. So this really surprised us. And we still don't have a really good explanation for what caused this. But this is the sort of dynamic behavior that we're interested in continuing to observe in this system to try and understand what's going on better. And since then, here's all the photometry folded on a slightly different period, now 104 days, just to kind of line up the very first transit and the very last two transits we've observed. And arrows are drawn to show you how the occurrence times of these transits can shift quite a lot between successive orbits. Potential explanations here are we have debris in two different periods. So similar to 1145, which shows debris on different orbits between 4.5 and 4.9 hours. Maybe we have a similar situation here, but we can kind of rule against that by the fact that we've only ever seen one dip at a time. We've never seen sort of two dips next to each other, closely spaced. So we would need to also explain why certain dips are disappearing if we want to attribute this dip to a different chunk of debris. But also 1145 shows a lot of variation in dip structure just between orbits. So potentially this is the same, we could be seeing two different chunks of debris kind of changing their activity levels over time. But again, that would sort of suggest you would see occasionally two dips closely spaced. So in other words, you need to explain why this dip here suddenly disappeared and was not observed, while this dip here suddenly appeared, but was not observed the orbital cycle previous to that. The other possibility is that this object, the debris as it comes close to periastron, if it's undergoing collisions or some sort of additional tidal disruption events, that could be altering the orbital configuration to some degree. I'm also showing, so this box here is showing a zoomed in panel on the right. And this is just to show you how potentially the depths of these transits can vary between different observations. So this transit here was relatively shallow compared to the others. But what we see if we kind of zoom in here is that there's actually quite a lot of variability happening within the dip itself. And so depending on when you observe, you might see a really deep transit down here, or you might see a really shallow one. We've gotten high-speed photometry in some of these dips. So again, showing just a really, really zoomed in panel here on the right for just 7 hours of photometry from McDonald Observatory. And we do see dips that are quite deep and last only about an hour, which sort of matches the variability that we see in our more, sorry, here's my timer. It sort of matches the variability we see in our more long time scale monitoring from the Las Cumbres Observatory and from ZTF. In addition, we're getting multicolor photometry. So this has been done for 1145 to try and constrain the particle size distribution. And similar to those observations, we've yet to see any color dependency due to the transiting material itself. And that's only with the G, R, and I bands, so our constraints are not super strict, but do limit the particle size to greater than 0.25 microns. And this, again, suggests, similar to 1145, that a lot of the small particles are potentially being sublimated out of this system pretty rapidly, which would also suggest that this debris is coming close to the white dwarf at periastron in order for that to happen. And lastly, I just want to mention this object, which we recently discovered, again, using Gaia and ZTF to identify it first, and then we followed it up pretty extensively. So we have on the left here another folded light curve with McDonald photometry from 2 separate runs in December of last year and February of this year. This one is much more similar to 1145 in terms of its orbital periods of around 9.9 and 11.2 hours, and also shows pretty dynamic orbit to orbit variations in the dip structures. And over the course of 2 months, those structures can change almost completely. And you see where you used to see dips, the phases of those dips have changed, or those dips have migrated or changed in depth to some degree. But what also makes this system different is that we see circumstellar absorption, but it's very narrow instead of the very broad circumstellar absorption we see with 1145. We're not exactly sure yet where that circumstellar absorption originates from, but we plan to get follow-up observations with sort of simultaneous photometric and spectroscopic observations to try and constrain that more definitively. But what's also peculiar about this system is that this is a very cool white dwarf, just 7,600 Kelvin. And the equilibrium temperatures for dust or larger bodies around this object are quite cool and sit in a regime that's right in between the sublimation temperatures of icy bodies and the sublimation temperatures of more rocky bodies composed of silicate materials. So we aren't exactly sure what is the physical mechanism that allows these dips to persist over long periods of time. Potentially, you can have cooler equilibrium temperatures if there's a dust disk that is occulting some of the stellar flux, which would lower these temperatures significantly down to like less than 200 Kelvin or close to 100 Kelvin. But yeah, it's also possible that collisions are sort of the predominant mechanism here and something that needs to be explored further. And I think that's pretty much it. I'll just sort of leave my conclusions here, summarizing, that these time domain surveys are really driving the ability to discover more of these systems right now. And obviously, once we find them, we need additional photometry and spectroscopy to characterize them better. But we're finally working towards being able to define these systems as a class and understand their physical mechanisms better throughout a wide range of evolutionary stages in the tidal disruption or rotational breakup or whatever physical processes is causing these systems to break up into planetary debris. And yeah, I'll leave it at that. Thanks.
Thanks, Zach. Very interesting talk. We already have a few questions in the chat. The first one is from Thomas Kupfer. If you can decide on an ideal sky survey cadence for this study, what would be your preferred cadence to do this work most efficiently? And the second part of the question is, with the current data, where do you think are your biases and which systems do you think you might miss and why?
Oh, good questions. Yeah, so my preferred cadence, I think, would be nightly for systems like these. And so the way we've designed our Las Cumbres observatory monitoring is to do it nightly, if possible, and also to have groupings of exposures that are more closely spaced in time. So ZTF uses, I think they do G and R exposures that are spaced apart by at least 40 minutes or so. But we really would like to know for these, especially the long period systems, how much they might be varying on short time scales, and for the short period systems as well. So if we want to find both in equal measure and be able to characterize them more easily with ZTF data alone, I think a nightly cadence with more closely spaced observations within the night would be pretty helpful. And in terms of biases, so I'll go back to this slide. Yeah, so we currently spend quite a lot of time identifying these systems because we need time series photometry at relatively high speeds, especially to find the short period systems. I think ZTF is probably better characterized to finding the long period variables, especially if you end up using metrics like these, which tend to distinguish long period variables a little bit better. So that could be causing some significant biases in our sample. Obviously, we're only looking at the top 1% so far, so we're just finding the most variable transiting debris systems. And it's not necessarily a given that they would all be there in the top 1%. I think, for instance, this bottom object is not very variable in the ZTF photometry or with the McDonald photometry, but Gaia picked up on it for some reason. So yeah, we need to find a way to potentially expand outside of the top 1% and find these more efficiently before we can really know, like, or answer questions about, for instance, like the space density of these systems and how common or rare they actually are.
Thanks, Zach. The next question is from Harvey Hischer. Have you looked for infrared excesses in these objects?
Yeah, so we typically check all of the available photometry that's out there for all of these systems. For most of the long period systems shown here, like the top 4, so far we have not found any infrared excess for any of these. So that's kind of surprising. We've also gotten spectroscopy for most of these, and only the first object on the top shows any metallic absorption. So those are other things that we don't quite understand. They don't sort of fit in with the paradigm of these transiting, of at least the first system. You know, you would expect if there's transiting planetary debris that it should be accreting onto the white dwarf, and you would see it in the atmosphere. But for these top 4 systems, we really don't see that. But in the short period systems, we see it much more commonly. I think all of these systems on the bottom 4 are pretty heavily metal polluted in their atmospheres. So that's another characteristic difference between the long period and the short period systems.
Thanks. And one last question by Tim Cunningham, who points out that as the sample is growing, it would be interesting to probe properties as a function of cooling age. Do you have any ideas or intentions to probe the ZZ instability strip for transiting systems too, avoiding the 150 megayear gap in the sample?
Yeah. So, yeah, like I said, it's hard to, like, there's a lot of variables in here. We have done follow-up for a lot of the ZZ studies. As you can see, one of them is in the instability strip, and in fact, this system is a pulsating white dwarf as well. So its Gaia photometric temperature is too cool, and its spectroscopic temperature pushed it into the instability strip. So we are probing there too. We don't want to just look over those, but it'll be a lot harder to find them in there if they are short period variables, because we'd have to sift through all the ZZ studies. Potentially that's where these metrics can come in handy too, and help us identify objects in the instability strip that actually are good candidates for transiting debris more quickly. But I haven't really systematically looked at properties as a function of cooling age yet. And so, yeah.
thanks, and thanks for the talk. I think now we'll then move on to the coffee break. I'll stop the recording.